Hey everyone, and welcome back for another deep dive with us. Today we're going to be tackling a really fascinating area. It's AI-aided drug discovery, but we're going kind of specific with it. We're going to be looking at a challenge called deep imbalanced learning. And our guide for this whole thing is a research paper. It's called ImDrug, a benchmark for deep imbalanced learning in AI-aided drug discovery. And it's authored by Lanking Lee, who's a senior research scientist over at Tencent AI Lab, and a whole team of other
Yeah,
experts.
they've assembled a really great team for this one.
They really have. And, essentially what they're trying to do is they're trying to figure out how to make AI better at finding new drugs,
Mhm.
which, as you can imagine, it's a lot harder than it sounds because of imbalanced data.
Right, and that's exactly what can throw AI models off. Like, imagine you're trying to train an image recognition AI, and the data set you're using, 90% of the images are cats, and there's only a few images of dogs. That AI is going to be amazing at spotting cats, but it might completely miss the dogs.
Yeah, that's a great analogy. So how does this whole cat and dog problem, how does that actually translate into drug discovery?
Well, in drug discovery, these AI models need to learn from these massive data sets. They're full of molecules and proteins and chemical reactions. The thing is, some chemical structures, some reactions are way more common than others. So if the AI only ever sees the cats, it might miss those rare dogs. And those dogs, they could actually hold the key to like brand new treatments.
Right, and missing those dogs, that could be a really big setback, especially given how much time and money goes into developing new drugs.
Yeah.
Paper actually mentioned it takes over a decade and something like $3 billion to bring a new drug to market.
Yeah, that's right. And AI has huge potential to really speed that process up and reduce the cost significantly, but only if it can handle this imbalanced data
Yeah.
effectively.
Yeah, so that's where UmDrug comes into play. So UmDrug is kind of like a testing ground for these AI models, but what exactly are they testing?
So they're testing how well the AI models perform all these different drug discovery tasks, but they're doing it when the AI is faced with four different types of data imbalances.
Yeah.
And these tasks include things like predicting drug side effects, identifying promising drug targets, optimizing chemical reactions, all kinds of different things.
So they're really putting these AI models through the ringer. The paper even has a visual figure one, and it shows this really uneven distribution of data in all these different tasks.
Oh,
One that really stuck out to me was predicting the catalyst type in a chemical reaction.
oh yeah, that's a really good example because certain catalysts are literally thousands of times more frequent than others. And that can really bias the AI model to just always predict the common ones and
Right.
completely overlook the rarer ones that might actually lead to those big breakthroughs.
Right, so it's almost like you're trying to find a needle in a haystack,
Hmm.
because the haystack is filled with, like, useless needles,
Yeah.
and the AI is struggling to identify the few that are valuable.
Yeah, that's a great way to put it. And just to make things even more complex, ImDrug actually includes 11 different data sets, each one with its own characteristics and its own challenges. So that diversity makes sure that these models are really tested on a wide range of scenarios, and it pushes them to their limit.
Yeah, so it really separates the AI wheat from the chaff, so to speak.
Exactly. And to make the evaluation even more rigorous, they've actually introduced two brand new performance metrics, specifically to account for this data imbalance: balanced accuracy and balanced F1. And those give you a much clearer picture of how well the models are actually performing, unlike the traditional metrics that can be really misleading when you're dealing with imbalanced data.
Yeah, so they're not just throwing different models at the problem, they're changing the rules of the game to make sure the evaluation is fair and accurate. But what about the models themselves? What kind of strategies are they using to tackle all of these imbalances?
So the paper explores three main categories of approaches: class rebalancing, information augmentation, and module improvement. And each one kind of offers a different way of approaching the problem. And they're all tested against the ImDrug benchmark to see what works best in each situation.
Okay, so let's unpack each of those categories one by one, starting with class rebalancing. What's the thinking behind that approach?
So class rebalancing is all about tweaking the learning process so that the AI pays more attention to those rare data points. It's like saying, hey, AI, those dogs over there, they're really important, even though there aren't that many of them, so make sure you learn about those too.
So you're essentially trying to level the playing field by giving more weight to those underrepresented categories. What about information augmentation? How does that work?
So with information augmentation, researchers actually create synthetic data, and they use that to boost the representation of those minority categories. It's kind of like taking those few pictures of dogs that you have and creating variations of them to make it seem like there are way more dogs in the data set than there actually are.
So you're basically creating a more balanced data set artificially. That's really clever. And lastly, module improvement. What's going on in that category?
So module improvement is all about designing AI architectures that are inherently better at dealing with imbalanced data. So instead of just tweaking the learning process or adding more data, it's actually changing the fundamental structure of the AI model itself. So it's more sensitive to those rare data points.
So it's almost like you're giving the AI a superpower. That allows it to see those dogs more clearly, even when they're surrounded by all those cats.
Exactly. Now, the researchers, they tested all of these approaches on the ImDrug benchmark, and what they found was, well, that's a story for part 2.
I'm on the edge of my seat. I can't wait to dive into those results. We'll see you in part 2, everyone.
Welcome back to our deep dive on ImDrug. Now, before we went to that cliffhanger, we were talking about all the different strategies researchers are using to deal with imbalanced data. When it comes to AI-aided drug discovery,
Right, like class rebalancing information, augmentation, module improvement, they all sound pretty promising in their own ways.
yeah.
But which one actually came out on top?
Well, the results are in, and it turns out there's no single winner. Different approaches work best, depending on the specific data set and the task at hand. It's kind of like a toolbox, you know. You wouldn't use a hammer for every job.
Right.
Sometimes you need a screwdriver. Sometimes you need a wrench.
So it's all about picking the right tool for the job. Makes sense. But I'm sure they found some pretty valuable insights from all this testing. What were some of the standout findings?
Well, one interesting takeaway is that deep learning techniques generally outperform traditional machine learning methods when they're specifically designed to handle imbalanced data.
That's not too surprising. Deep learning's known for its ability to handle these really complex patterns, so it seems logical that it would have an edge in these scenarios.
Exactly. But even within deep learning, there wasn't one technique that really stood out above all the others.
So it's really about understanding the strengths and weaknesses of each technique and choosing the right one for that specific challenge.
Precisely. For instance, one technique that really caught my eye was called BBN, which stands for Bilateral Branch Network.
BBN. Catchy name. What's so special about it?
It's a pretty clever technique. It essentially creates two branches within the AI model. One branch actually learns from the overall data distribution, while the other specifically focuses on those rare data points. It's like having two detectives working on a case. One have that broad overview, and the other one specializes in tracking down those really elusive clues.
Oh, interesting. So how did this two-pronged approach perform?
It performed pretty well, especially in these long-tailed classification scenarios. However, there were some instances where it struggled, particularly when the data imbalance was super severe. So it highlights the fact that even these really sophisticated strategies can't always fully compensate for the challenges of skewed data.
Yeah, it's like you're trying to teach an AI to identify different types of birds, but you only showed a handful of pictures of the really rare species. Even with the best algorithms, it's going to have a hard time learning if it just hasn't seen enough examples.
Exactly. And it really underscores the need for continued research in this area. ImDrug is a huge step forward, but there's still a long way to go. We need to develop even more sophisticated techniques and strategies to ensure these AI models can truly excel in these really challenging scenarios.
Now, the paper also mentioned something called scaffold splitting and temporal splitting. What are those all about, and why are they important?
Yes. Those are alternative ways of splitting the data. For training and testing, traditionally in machine learning, you would just randomly split the data. But with imbalanced data, that can be problematic.
I see, because if those rare data points are scattered randomly, you might end up with a training set that's completely missing crucial categories.
Exactly. And that leads to a biased model, so scaffold splitting addresses this by grouping molecules with similar structures together. So this ensures that structurally similar molecules will end up in either the training set or the testing set. And this prevents the AI from simply memorizing specific molecules.
So it's like teaching the AI to recognize bird species based on these shared characteristics, rather than just their individual appearances.
Precisely. And temporal splitting, that's used for data sets that have a time component, like chemical reaction patterns. And it involves splitting the data based on when it was published. This actually forces the AI to learn from past data and then try to predict future trends.
Well, that's interesting. It's like testing the AI's ability to anticipate new developments based on that historical information. So how do these alternative splitting methods actually affect the AI model's performance?
Wow, this is fascinating. They actually led to a decrease in performance.
So they're making the task harder for the AI. Why would they do that?
It's all about creating more realistic and more challenging scenarios that better reflect the complexities of real-world drug discovery. By pushing these models beyond their comfort zones, researchers can get a more accurate picture of their true capabilities and identify areas where there needs to be further improvement.
Right, so it's like taking those bird-identifying AIs
Yeah.
out of the classroom
Yeah.
and into the wild, where they have to deal with all kinds of variations and unexpected situations.
Exactly. And this rigorous testing is crucial for building trust in AI-aided drug discovery. If we want to rely on AI to accelerate the development of new treatments, we need to be confident that these models can actually handle the messy realities of real-world data.
Now, before we move on, I want to circle back to those two new evaluation metrics that you mentioned. Balanced accuracy and balanced F1. You said they were designed to kind of address the shortcomings of those traditional metrics. Can you elaborate on that a little bit?
Of course. So traditional metrics like accuracy, they can be really misleading when you're dealing with imbalanced data. They tend to favor the majority class, and it can give you a false sense of how well the AI is actually performing.
Right. It's like judging that bird-identifying AI solely on its ability to identify pigeons, which are everywhere,
Right.
without considering its accuracy in identifying those rarer species.
Precisely. Balanced accuracy and balanced F1, on the other hand, take into account the performance on both the majority and the minority classes, providing a much more comprehensive and balanced evaluation.
So it's like judging the AI on its ability to identify all bird species equally, make sure it's not just a one-trick pony.
Exactly. And the ImDrug paper highlights just how important these balanced metrics are. Some AI models that scored really high on traditional metrics showed a significant drop in performance when they were evaluated using balanced accuracy and balanced F1.
So it's kind of exposing those AI models that are just coasting on those easy cases and revealing their true colors. When they're faced with a more balanced assessment,
That's a great way to put it. And it really underscores the need to move beyond those simple metrics and embrace more sophisticated approaches that accurately reflect the complexities of the data and the tasks at hand.
this deep dive has been incredibly enlightening. We've explored the challenges of imbalanced data in AI-aided drug discovery, examined the ImDrug benchmark, and we delved into the various strategies for training and evaluating these AI models in this really demanding field.
We have covered a lot of ground, and in the final part of our deep dive, we'll explore the broader implications of this research and consider what the future holds for AI in drug discovery.
Looking forward to it. See you in part 3, everyone. Welcome back, everyone. So if we spent the last 2 parts really unpacking ImDrug, this fascinating research into AI and drug discovery. We talked about the challenges of imbalanced data and all the different strategies that researchers are using to overcome them. But what does all this mean for the future of healthcare? What's the big picture here?
Well, that's the really exciting part. ImDrug isn't just about tweaking algorithms or anything. It's about laying the foundation for a future where AI can completely revolutionize how we develop new treatments. Imagine a world where AI can just sift through all this data, mountains of data, and identify those really rare but crucial discoveries. That could lead to cures for diseases that right now we don't have any effective therapies for.
It's like having this army of superpowered researchers working tirelessly to uncover those hidden gems that might have gone unnoticed otherwise. That's a pretty compelling vision. But what specific advancements can we actually expect to see in the coming years?
Well, I think we're going to see a huge surge in research, specifically focused on creating AI models that are just inherently robust to data imbalance. So that means developing new algorithms, new training techniques, and new evaluation metrics that are specifically designed to handle all these complexities.
So it's not just about using the tools we have more effectively. It's about building entirely new tools that are tailored for this very specific challenge. And as these new tools emerge, what kind of impact would they have on the whole drug discovery process?
Oh, the potential is just enormous. AI is going to be able to analyze not just molecular structures and chemical reactions, but also patient data, genetic information, environmental factors, you name it. This is going to lead to a much more holistic and personalized approach to drug discovery, where treatments are specifically tailored to each individual patient based on their unique profiles.
Wow, so it's almost like having a custom-designed drug for every single person based on their specific needs and their circumstances. That's incredible. But with all this talk about AI, it's easy to forget that drug discovery is still a very human endeavor. So what role will human researchers actually play in this AI-driven future?
That's a really important question. AI is not meant to replace human researchers. It's meant to empower them. Think of AI as like this really powerful assistant that's capable of handling those really tedious and repetitive tasks. And that frees up the human researchers to actually focus on the big picture, asking the right questions, designing innovative experiments, and interpreting those complex results.
So it's more of a collaboration, a partnership between human ingenuity and artificial intelligence. That's reassuring because I think there's sometimes this fear that AI is going to take over completely and leave humans out of the loop.
I totally understand that fear. But I really believe that AI, when used responsibly and ethically, has the potential to just augment human capabilities and unlock breakthroughs that we wouldn't be able to achieve otherwise.
That's a very hopeful perspective. And I think it aligns with what we've learned about ImDrug. It's not about replacing human researchers. It's about giving them better tools and better insights so they can make more informed decisions and ultimately accelerate the development of those life-saving treatments.
Exactly. And I think that's the key takeaway from this whole deep dive. ImDrug represents a pivotal step forward in addressing this fundamental challenge in AI-aided drug discovery. It's really laying the groundwork for a future where AI and human ingenuity work together to advance healthcare and improve human lives.
That's a fantastic note to end on. Thanks for joining us for this fascinating journey into the world of ImDrug and deep imbalanced learning. We hope you learned something new today and that you're as excited as we are about the future of AI in drug discovery. And we'll see you next time for another deep dive.